I'll just do a very quick introduction of Lorenzo, who's our guest today at the Phi-Lab, who works as a researcher in Tor Vergata University in Rome, and who's going to be talking about physics-based AI for SAR-based retrieval models.
Thank you, Monia, for the introduction. I jump directly on the agenda. No, I'm not jumping on the agenda. No. Okay, thank you. So just come back to the agenda, please. The slide before. Okay, just I give you a brief introduction about me, and then we're going to analyze the Earth observation retrieval models from traditional approaches like physical models to AI and their integration, which is the main topic of this talk. And then we're going to analyze the challenges in estimating soil moisture from SAR data. And I'm going to show you a couple of works on physics-based AI for soil moisture estimation. The first one uses the Tor Vergata model, electromagnetic model, over cornfields. In the second one, which is the work I had the opportunity to work on during my visiting a jet propulsion laboratory, is focused on optimizing the radiative transfer model using a physics-informed deep learning network. And then the final remarks. Okay. About me, I got the PhD in geoinformation at the University of Tor Vergata, where I'm currently a researcher. And I'm involved in research and development activities and also teaching activities. My, let's say, field of study lays on SAR data processing, soil moisture estimation with physics-based AI. I had the opportunity to do some visiting experiences here at ESA for the master thesis, and then a jet propulsion laboratory for the PhD visiting. And also I contribute within research and development activities with two spin-offs of University of Tor Vergata, GeoK and Blue Dot. And we can move on the next slide. Okay, now I'm going to introduce you the topic. So the Earth observation retrieval models. Let's start from the concept behind estimating biogeophysical parameters from space. So we start from the forward problem, so the forward modeling, in which we simulate how electromagnetic radiation interacts with the Earth, with the surface, predicting what the sensor detects. So basically here we start from the state of the biogeophysical variables on the Earth. We have also omega containing a set of the sensor configuration, so the wavelength, incidence angle, frequency, polarization. And through the forward model function, we get the measurements obtained by the platform, in this case by the satellite, like, for instance, the backscatter. Okay, thank you. And when we invert the model, so we switch from the direct problem toward the inverse problem, what we do is to estimate the biogeophysical parameters starting from the measurement obtained by the satellites and a set of inversion model parameters. So here is the challenge, to find the inverse model to estimate the parameters. So we start from the satellite acquisition. We preprocess data. Then we need a processor that is able to extract the information we need. In this case, biogeophysical parameters estimation, like soil moisture or biomass, vegetation biomass, and so on. Typically, we have these three methods: the empirical, the physics methods, and the data-driven methods. Concerning the empirical ones, they are simple to be implemented and computationally efficient, but they are too much site-dependent, and quite often they are not able to capture the highly nonlinear relationships behind the phenomenon we are observing. Concerning the physical methods, they are physically consistent, of course, and provide, let's say, explainable results, interpretable, and they are also very useful, the physical models, to generate synthetic data. Since for instance, in soil moisture estimation problems, it's difficult to find high quality labeled data. Physical models can help in this, generating synthetic data sets. However, they are ill-posed inversion because we start from a few observations like the scattering different polarization. But in the inversion process, we have a lot of parameters to estimate, not only soil moisture, but also concerning the surface, the roughness, and concerning the vegetation, the structure, the vegetation water content, and so on. Then we have data-driven methods like machine learning and deep learning. They can map highly nonlinear relationships, and they have a high generalization and data fusion capabilities. But however, they are often used as black boxes. So a lot of users select some relevant input features, feed into the machine, and expect good results. And sometimes they obtain good results, but if something goes wrong, they don't know nothing. We don't know nothing about what's going on in the machine. So, and also they require high quality labeled data sets for this kind of application. So here we have two sides. On one side, we have the white box, which comprises the physical models, the physically consistent results, and then the black box, the data-driven methods. As you can see, the data size increases going toward the black box because we mentioned it. We need a lot of data to train the model, while the interpretability increases while we come closer to the white box. So what we can do is to take the best of the two worlds and put ourselves in the gray region and merge the generalization data fusion capabilities of AI with the physical consistent, of course, of the physical models. So these physics-based approaches can be let's say, implemented in different ways. So the first one is at the dataset level, is also called as observational bias. And here the physics is used to generate synthetic training data. So, for example, we can, as I mentioned before, we can use AI to invert the model, starting from the synthetic dataset, or we can emulate the radiative transfer model, so solve the direct problem. And a typical workflow is to generate the dataset with the radiative transfer model, and then we take this synthetic dataset to train an AI algorithm to do the retrieval. Another way is to put ourselves at the integration at the architecture level, or it's also known as inductive bias. So here the architecture is modifying a way so that the physics is embedded directly in the architecture through some physics layers. And typically what we can do is to put some physics layer between two AI models. So for instance, trying to estimate some parameters with AI, starting from the observation, then putting these estimated parameters in a forward model, like the integral equation model for bare soil, and then take the output to do some other estimations. Or we can have also the fully coupled hybrid networks in which we have more than one layer, and the AI layers, the deep learning layers, and the physics layer are completely integrated and interconnected. The third way is to put the physics at an optimization level, so with a learning bias. In this case, the physics is introduced through the loss function. For instance, we know the physics inform the neural networks. In this case, the physics is inside the loss function, and it can be expressed with some physical constraints, or maybe also integrating radiative transfer model inside the loss function. So the loss function becomes a physical model. Okay, so here we talk also about explainable AI. We have to discriminate between scientific and algorithmic explainability. The first one focuses on explaining the outputs of our AI framework using the physics laws. So we can extract some intermediate products which are useful to check if they are physically consistent or not. So we can understand how the model can align with the physics behind the phenomenon we are observing. In the case of algorithmic explainability, instead, we are trying to explain how the model works internally. That it's not so easy, but there are some explainable AI tools that can be useful for this to accomplish this task, and we can do some feature importance, some feature engineering, so understand which input features are more relevant with respect to the others, and then we can also extract some activation or saliency maps. The difference here is basically can be mapped through the scientific and algorithmic explainability. With the activation maps, we can look at the different layers of the AI framework and extract some, as I was mentioning before, some intermediate products, trying to understand which layers contains higher or lower activations. In the saliency maps, instead, we are focusing on the output or in the let's say in the input to find some important regions or patterns that can be extracted from data. Let's jump to the challenges in estimated soil moisture, just to recall that soil moisture is an essential climate variable declared by the Global Climate Observing System, since it impacts climate, agricultural productivity, forestry, and ecosystem health. Because it's a driving factor, is a proxy of risk of drought, fires, and forest health, floods, landslides, infrastructure stability, and of course agriculture, which is the topic we are focusing on today. Through soil moisture, we can monitor and avoid plant water stress events, occurrences. We can manage resources, water resources, with smart irrigation, and we can help to maximize the crop yield, also trying to estimate the crop yield. To measure soil moisture, there are, of course, the traditional approaches based on collecting in situ measurements to the probes in the terrain. But as you can imagine, they are resource intensive and they are punctual information, not specialized. And of course, they are costly. We can use the satellite data. This is the good news. Optical sensors are limited, of course, by the cloud cover. And also they are, let's say, limited by the fact that in agricultural fields we have vegetation layer on the ground, so we cannot assess the condition of the ground. So the most popular approach is to leverage synthetic aperture radar data, and this is because SAR data can provide a spatialized information and also a continuous monitoring to build soil moisture time series. And because SAR data and radar data are have a strong sensitivity to geometrical and dielectric properties of the target. This is a plot from the Ulabi book, which shows the relation between soil moisture changes and backscatter coefficient, and we can see that in different polarizations we have a correlation between soil moisture and SAR data. But this, of course, refers to the bare soil case. So as I was mentioning before, the main challenge is the presence of vegetation. So the SAR signature in presence of vegetation is a mixture of scattering mechanism, different effects. In the bare soil case, or if the wavelength is penetrative enough to interact with the soil, we trigger the surface scattering mechanism. And in this case, the received signal depends mainly on surface roughness and moisture. Then we have the volume scattering, in which basically the E-signal interacts with the top canopies of the vegetation. So here we don't have, or we have a weak sensitivity to soil properties. And then we have double bounce scattering or dihedral scattering, in which the signal interacts with both vegetation layer and surface. But especially here, it's very difficult to disentangle the two effects. So to deal with this complicated scene, so soil with vegetation on top, some physical models were developed. For bare soil case, the Kirchhoff small perturbation model and integral equation models were developed. And for vegetation modeling, we can divide the models in empirical, theoretical, and semi-empirical. The most popular one is the water cloud model, which basically models the vegetation as a water cloud on top of the surface, and the properties of this water cloud are rely on typically on NDVI, and most of the times one multispectral index is not enough to describe the vegetation structure and properties. There are also some models which are much more descriptive, like the Tor Vergata model that was developed at my university. At my university, and in this case we have the surface layer, which is modeled with the integral equation model, and then we have the vegetation, which is modeled very specifically to a crop type. So in this case, we are referring to corn. We have a layer filled with vertical cylinders to represent the stalks of the plants, and then we have the top, the canopy layer, which is filled with small scatters of simple shape, like disc and cylinders. And also this upper layer is subdivided in thin layer, and then the wall. Then I'm coming back to this later in the slides to describe how it works. But you can understand that the modeling here is much more complicated than the water cloud. Okay, on the other hand, we are entered in the golden age of SAR, so we can cover basically the entire microwave spectrum with the sensor we have now in orbit, from P-band biomass to L-band SAOCOM and NISAR, and C-band Sentinel-1 and X-band Cosmos Skymed. So of course we can choose based on data availability, but of course based on the task, the right sensors. So for instance, if we want to estimate soil moisture in forested areas, we would choose P-band, which is much more penetrating signal. If we are in a bare soil case, we can use C-band Sentinel-1 or X-band Cosmos Skymed. For agricultural areas, L-band seems to be the most appropriate. So okay, so you saw that we are plenty of SAR data, and also the in situ measurement campaign are increasing and increasing. So we can leverage this vast amount of data to train AI frameworks, starting from machine learning models and going to deep learning and deep learning dealing with the
For some reason, we lost you. I don't know if they are still connected. Ruben, Lorenzo. For some reason, we lost you. Okay, they are reconnecting. Sorry.
Can you hear me?
Yes, now yes. We cannot see the screen shared, but we can hear you.
Yeah. Now you should see the screen. Yes. Okay.
Yes.
So okay. So basically, we had physical models approaches, and then the AI approaches. Again, I come back to this slide to the integration of the two methods, because now I'm going to show you some results from two works. Basically, adopting in the first work the integration at the dataset level. So in this case, we explored the physics-based AI methods using the Tor Vergata model. We started from the calibration of the Tor Vergata model. So I wanted to show you this part of calibration because it's part of the process when using such descriptive physical models. Then we generated with the calibrated model a simulated SAR dataset to train a multi-layer perception for inversion and retrieve soil moisture. Of course, not only estimated soil moisture, but trying also to disentangle the different scattering mechanisms. And then we try to test on satellite data. For the second work, instead, we applied the integration at the optimization level with learning bias. So we started from dataset collection. In this case, we used SAR data in addition to other remote sensing data, and also soil moisture measurement, of course, for target for the supervised learning. And we trained the physics-informed residual network to estimate soil moisture and analyze the results. Also here, trying to disentangle the different effects. Okay, so let's start from the first work. So here I come back to the Tor Vergata model to give you a more detailed description. So it's based on the radiative transfer theory applied to the discrete scatterers I was mentioning before. So disk and cylinders that have specific absorption and scattering properties to model the vegetation structure. The model takes as input the sensor configuration, so incidence angle, frequency, and polarization, and soil properties, which are basically here in this model described by roughness and soil moisture. And then also taking as input vegetation parameters. Here in this model, we have a routine called growth model, which takes as input the height of the plant, and then describes all the single scatters, their shapes, their orientation, their dielectric properties accordingly to the height of the plant. Of course, these relations are fitted on on-site measurements. As I was mentioning before, all the system is divided in layers, and the model applies the matrix doubling algorithm. So it computes basically the scattering matrix from the soil, and then from the vertical stalks, and then on the top canopy. As you can see here, the top canopy is subdivided in thin layers. So the matrix doubling algorithms compute all the attenuation and scattering effects of any order between the different layers. So we can try to reconstruct the path of the signal inside the whole system. And at the end, also the three main layers are let's say computed together to obtain as output the total backscatter. But since it's also a fully polarimetric model, we can extract the covariance matrix. And here the total backscatter is computed as the sum of the different components. So we have the scattering coming from the soil, the one coming from the volume, and then we have the double bounce, which is the combination as I was showing before, and multiple scattering, which are all the higher order interactions. For the calibration, we focused on we do some projects. We work on some projects focusing on Argentinian corn and Italian corn, and we used SAOCOM L-band data and Cosmos SkyMed X-band data, and basically in the in-situ measurement we can find soil moisture and some plant parameters to fit that growth function I was mentioning before. So to find the relation, for instance, between height and plant water content. And also in some cases, we had also the soil roughness. When we don't have, for instance, soil roughness, we should do something more advanced. So we can try to find the optimal soil roughness to characterize the different fields, the different plots in the scene. So here, for instance, we can compute the difference between the simulations performed with different values of soil roughness and comparing them with the observed backscatter and see which is the soil roughness value that minimizes the difference. So in this way, we can fill this gap, this data gap. Also, to fill data gaps, we can find some relations. For instance, here we derived the growth stage starting from the days from sowing. It strongly depends on the data set we are dealing with. So sometimes we can have the days from sowing. We can compute the days from sowing, but we don't have the growth stage. Or sometimes in some data set we have the height of the plants. Otherwise, we have to derive it while fitting these curves. And also to build that growth routine, so to characterize all the properties, geometric and electric properties of the different scatterers, we use allometric equations. Also in this case, in situ measurements are required. So for instance, in this case, we have data recorded, which are referring to the plant water content, and we find the relation with plant height, so that the models can take as input only the plant height, and then assign the plant water content to the disk, to the cylinders, all the scatterers, modeling the vegetation. Okay, at the end of the results of the calibration is a comparison between what we can model with the radiative transfer model and the observed SAR signature. In this case, we are comparing the backscatter. So here on the left, we are referring to the results obtained on the Argentinian site. And here on the right, we are comparing the simulated and the observed backscatterer for SAOCOM L-band and Cosmos SkyMed X-band. And also this comparison can be done through a scatter plot or through time series. So for each field, we can try to find matches between simulated values and observed values. Okay, now let's deep dive in the methodology. Basically, the methodology for this work was inspired by this study made by Irena Heinzek from the lab, and it's a two-step approach. So in this study, AI was not involved, but with physical models, the flow is basically the same. So we start from SAR data, and with some scattering decomposition models, we derive the different components I was mentioning before, and then we use the different components, or a subset of them, to estimate soil moisture. So basically, this was the idea behind our work, but to perform this task, the estimation of the scattering components and the soil moisture retrieval, we adopted AI models. So we started from basic structure. So we have three models here now. I'm going to describe them. They are M1, M2, and M3. M1 is the simplest one. And here, basically, we start from input parameters over the core field. Here we have the frequency, incidence angle, roughness, and here we have soil moisture. We basically generate a synthetic dataset with while varying soil moisture values, soil roughness values, the plant heights, also to cover all to make the model as much generalizable we can. So we use the Tor Vergata models to generate the synthetic data, which consists of covariance matrices and the not attenuated components. Here we have surface and double bounds. So basically we have the total backscatter, the total SAR signature, and the sum of the components of the total. So here the volume is missing because the goal here was to remove the vegetation effects and to estimate the surface and double bounds, which are the most sensitive to the soil conditions, and then to use these two components as input for another machine learning model for devoted to soil moisture retrieval. Of course, for data preparation, we added some noise because we are dealing with the simulated domain. And since the final goal is to apply such a framework to real data, we added some noise and, of course, common practice steps for machine learning, input data normalization, and training, test, and validation split. And this is basically our input, is the covariance matrix. Here, there are some information about the network devoted to the decomposition. So the step 1, and we have also the step 2. So here they were represented only surface and double bounds, but we are dealing with the 3 different polarization. So we have the double bounds and surface at the 3 polarization, VH, VV, and HH. So basically we have 2 multi-layer perception. One is devoted to disentangle the effect, the scattering mechanisms, and the second one takes as input the output of the first model to estimate soil moisture. Then for the we decided to merge the two models in one single AI framework. So basically here the generation of dataset is the same. The inputs and output are the same. The only thing is that we are at each epoch trying to optimize both the task. Not we don't have a sequential approach, but it's a combined approach. So we have basically a combined loss, the decomposition one, trying to minimize the difference between the simulated components, this one, and the estimated components, and the other loss tries to minimize the difference between the actual soil moisture and the estimated soil moisture values. Then, since we try to apply M1 and M2 to real data, and the results were very bad. So when we are moving in the simulated domain, everything went smooth. But when switching domain from the simulated to the real one, regardless of the noise we added to the dataset, we had some problems. So a solution was to fine-tune the model on real data. So we try to validate the approach using a leave one out method. So basically here we have M2, and then after the training of M2, we fine-tune with some on-site soil moisture measurement, and real covariance matrices from SAOCOM L-band. And this is results after the fine-tuning. So we were storing computing the metrics root mean square error and Pearson on both the simulated images and the real SAOCOM images, and we were trying to understand how these metrics were changing when changing the number of fine-tuning epochs. So basically, when starting the fine-tuning, let's focus on the real data, which are the dashed lines. So the Pearson was increasing and the root mean square error was decreasing. So we expected this behavior, but after almost 140 epochs of fine-tuning, let's say both the metrics becomes more unstable. So here, for instance, the Pearson is continuing to increase, but then this is a polynomial approximation. So after this threshold, it becomes much more unstable, and this is because basically the model starts to forget what it learned during the pre-training. So when training with simulated dataset, so it's adapting too much to the real data. And here we have a scatter plot of the estimated soil moisture. So also here we try to feed the model during inference time with real SAOCOM images and simulated images. And here is the scatter plot using the model after 140 fine-tuning epochs. We can see that for yellow markers, which refer to the SAOCOM data, we obtain good results in terms of root mean square error and Pearson. So we have a significant improvement after fine-tuning. On the other hand, for simulated data that was working really good before fine-tuning, now we had not good results in terms of root mean square error and Pearson coefficient. And again, this deterioration is due to the real data adaptation. Okay, so I don't know if you have question for this part, or if we can go ahead and then.
You can go ahead.
Okay. So here another approach. So as I was mentioning before, this work was conducted at the Jet Propulsion Laboratory during my visiting, and it was related on optimizing the radiative transfer model using this physics-informed deep neural network. So here we have the physics in the loss function of the model. Okay, as we said, using physical models can bring some challenges because they are crop type dependent. So in the work we analyzed before, we were focusing only on corn. Instead, here for this work, we wanted to develop an algorithm able to run on different crop types, and also for some specific, some descriptive models like the Tor Vergata one. As I showed you before, during the calibration part of the model, we are relying too much on campaign measurements, which refer to one site. So when changing site, everything becomes much more difficult. And also, there is the challenge of switching from the simulated to the real domain, which can be, let's say, reduced with fine tuning, but also with sometimes it's not enough. So what we can do is to increase the level of information to be ingested by the AI framework. In this case, we combined, of course, physical models and AI, and we ingested also, as I was mentioning before, extra remote sensing data together with the SAR observables, and this defines the methodology. So we start from a physical model which provides the detailed characterization of the vegetation and soil properties. And since as I was mentioning before, the problem is ill-posed. The inverse problem is ill-posed because we have a few observations and a lot of parameters of the model. In this case, we decided to simplify the physical model. So here the task was to let the AI framework learn how to represent the vegetation and soil scene, the target scene, what is called the phase matrix. And here the model is very simple. We have the total backscatter, which is a combination of the different effects. So we have some parameters, the red ones, which are the one we want to estimate, optimize. PV relates to the volume scattering, PD to the double bounce, PT to the triple bounce, and then we have tau, which refers to the attenuation of the vegetation over the lower layers and the soil. And also we have the surface here, which is modeled taking into account the soil moisture, MV, and the two parameters, which are PSB and PSA. So basically, what we do is to take these SAR data and extra data to feed a residual network model. And the first task here, again, we have two tasks. The first one is to optimize the scattering components, and the second one is devoted to soil moisture estimation. So here, for the first step, this becomes the loss function. So basically, we adopt a Huber loss to minimize the difference between the observed backscatter and the reconstructed backscatter computed as the sum of the different attenuated components. Then between step 1 and 2, we apply physical constraints because what we did was to generate some simulation with the original physical model, and from them we derived some assumption that we wanted to impose to the system, and then I'm going to describe which physical constraint we are adopting. And then we switch to the second step, which is the one devoted to soil moisture estimation. In this case, we are not using a residual network or an MLP, but we are using a random forest, taking as input all the optimized parameters and retrieving soil moisture. Here, the choice was to, if you remember from the study I showed you before, we only selected the double bounce and surface. Here, instead, we wanted to consider also the vegetation, the volume scattering, and the attenuation to give also for the random forest a complete representation of the scene. And the entire process is repeated more than 100 times. So we have more than 100 models. And then we make an ensemble of these estimations. So here we have our input features. For SAR data, we consider L-band backscatter in HV polarization. This methodology was developed for NISAR data, and for NISAR we have HV and HH polarization. So we decided to use one of these polarization as input for the model, and one polarization to for the loss, which is the one here in the we are using to minimize this difference. Together with the SAR backscatter, we include the vegetation water content computed from MODIS, some information about the soil characteristics like clay, sand, and silt content, which are strongly related to the soil moisture, and then temperature and precipitation from ERA 5. Of course, then we resampled all the input to a common resolution, which is 100 meters. Also because we wanted to push to a finer resolution compared to the current soil moisture algorithms running for NISAR, which is 200 meters. So we wanted to do a step more. And we used the SMAPVEX 12 dataset, which collects in situ measurement from 11 available dates. Okay, yes, I can go ahead. Okay. This slide describes the first module, so the one devoted to the RTM optimization. So we adopted a ResNet because we wanted to leverage the skip connections to propagate the input information to each residual block. And we optimized this architecture with Optuna, trying to find the optimal configuration in terms of number of residual blocks, number of nodes inside the blocks, and so on. And so the optimal configuration appeared to be the one which comprises two residual blocks, each of them comprising 64 nodes activated by rectifier linear unit. And then we obtain at the end, so we start from the input features and we obtain the optimized parameters. Here we ingest the measured soil moisture, so the one collected in field. So we put the measured soil moisture here, MV. So we take the estimated parameters here, and we have the surface component, and we do the same for all the other components. So when performing the combination of these effects, we obtain the total backscatter reconstructed here, the predicted HH. And then we compared with the UAV SAR, which is the source of our SAR acquisitions, to minimize the difference between the observed and reconstructed backscatter. Okay, here, yeah, as I showed you before, in the workflow between step 1 and step 2, we apply these physical constraints. It's very simple. Basically, what we expect from the simulations is that the triple bounce, since it is a higher order interaction of the signal with the complete system, is the lowest, is the weakest components among all the components. So since sometimes the networks in that 100 and more models were swapping the different parameters. Sometimes PT, which we expected to be very low, was instead really high, or medium values. So what we did is to apply a physical constraint to discard all the models giving to the triple bounds too much importance. So at the end of this physical constraint, we obtained that half of the models were valid. So we used that models to train the results of that models to train the random forest algorithm and estimate soil moisture. So here again, the random forest model takes as input the optimized parameters plus the observed SAR HH backscatter. And of course, random forest gives us different prediction. We average all the predictions, and with 200 trees, we get the soil moisture estimation. Here, just to give you additional information about the sites, we were focusing on this region in Manitoba province in Canada, where the SMAPX12 campaign data were collected. And during the data collection, as I was mentioning before, UAVSAR data were acquired. So we have 11 dates which L-band backscatter acquisition are available. Also in this case, all the images are resampled to 100 meters to match the reference resolution. And here you can see that we have different land covers, different crop types. The major crop types are soybeans, canola, corn, and winter wheat. And here in red markers, you can see the soil moisture sensors, which provide us more than 8,000 samples to train the framework. Then we divide in training, validation, and testing. And here we have some results. So first of all, what we did was to, at inference time, compare the total backscatter observed by UAVSAR and the one reconstructed as the combination of the different effects. Here you can see that for this date, this is July 15, 2012, the patterns are quite similar, and also the mean value is quite similar in terms of backscatter expressed in dBs. But also we try to compare them with the data sample distribution and with a scatter plot. So here we obtain a root mean square error of 3 dBs, which is not really optimal because this, let's say, difference of 3 dBs can bring some huge differences in the target. So difference in the vegetation structure or in the soil moisture values can bring to this kind of difference. So this is quite good, but of course it can be improved. Okay, this is already the description I did. And here we have the different scattering components. So in the introduction, I was mentioning the fact that we can generate some intermediate products to assess the physical consistency of these intermediate products and make the model more explainable, more interpretable, and for sure more physical consistent. So here, just computing, applying the attenuation term to each scattering parameter, we obtain the different scattering mechanisms. So volume, double bounds, triple bounds, and surface. And we plot them again for July the 5th. And we assess the distribution of values in terms of mean values across the whole region, but also we did some samples check on some fields, and for instance, comparing taking some corn fields and comparing the different components with the RTM simulations. So since for this for the scattering components we don't have a ground truth, our ground truth for the comparison was the simulation with the radiative transfer model, the original one, not the simplified one. So in this case, we were able to compare the corn, soybean, and wheat mean values with the maps we were obtaining for that crop type fields. So here, comparing the data, we had a good agreement, except for the double bounce, which seems to be underestimated, especially for corn. And this is likely due to the fact that we have a strong presence of high volume crop types like wheat. So in this discrepancy lies on the training data set. And here we have the soil moisture result. So again, we generated a map for July the 5th of the soil moisture value, and then we compared the estimated soil moisture values with the measured ones by the sensors, and we obtain a root mean square error of 5.65%, which is quite good. And then what we decided to do was to assess the performances for different crop types. So, for instance, here we have corn, soybeans, wheat, and grassland, and we can see that the best results are for wheat, with a root mean square error less than 5% and a square R of almost 0.8. We have a slightly worse result for corn, and this is probably due to the fact that we were underestimating a bit the double bounce, and the worst results is obtained for grassland, but this is likely due to the fact that there is low. This class is underrepresented in the dataset with only 281 samples. And as a final step, so we basically published a paper with the approach I just mentioned. What we did is to move from a version 1 to a version 2. So if this was the approach I was referring in the previous slides, so 2 different steps with 2 different models, the RTNet, we called it the radiative transfer network, and the random forest for soil moisture estimation. Here in the version 2, we again, like in the previous case study, we merged the two tasks. So we still have 2 different modules, but they are strongly combined through a combined loss minimization. So here we have the loss one, which is basically the Uber loss computed on the simplified physical model I was showing you before. And then we have a classic loss for soil moisture, a mean square error, trying to minimize the difference between estimated in situ measurement. And these losses were combined with also some weighting coefficients, because what happens is that these 2 losses can have different magnitudes. So to put a regulation factor, we put a coefficient on top of one of the 2 losses to make them comparable and obtain good estimation of soil moisture while providing a good disentanglement of the different scattering mechanisms. And here I just put the comparison in terms of soil moisture estimation, switching from version 1 to version 2. So the test set was the same, but we got better results. So here we go lower than 5% root mean square error, and we increase also the square R. Final remarks. So here we I tried to show you that AI can boost physical models because can efficiently handle a vast amount of remote sensing data sets, also coming from different sensors, and to map and approximate highly nonlinear relationships. On the other hand, the physics improves AI, making it more interpretable, trustworthy, and through some intermediate products, providing physical knowledge from the AI framework. What I noticed during this research was that the true integration is key. So when combining physics and AI in a sequential way with separate blocks, we have some benefits, but they are limited. The true potential is expressed when we embed the physics inside the architecture. In this case, within the loss function. And of course, the objective of these works were to test and implement some approaches which can be the starting point from scientifically valid and operational workflows for Earth observation applications. In particular, since here you are doing a lot of work here at Phi-Lab on foundation models, which are task agnostic and multimodal. One of the limits of foundation models is that you can completely lose the physics behind what you are doing with the model. So you can fall in the risk of treating the model like a completely black box. So I think that I strongly believe that one strong point is to make the foundation models as much, let's say, explainable as possible to improve the robustness and the interpretability of the results. And okay, so this was my last slide. Here you have my email and a couple of QR codes of our university lab and the spin-off Blue Dot observation.
Thank you.
Thanks.
Again, sorry for all the technical problems.
No worries.
And since we were a bit over time, maybe we can prioritize the questions that we have online.
There is one question online. I mean,
and also, I mean,
just if anyone here has a question, we can.
I have a few questions, but I can ask them later. That's how you want.
So someone online asks, do we assume that the soil contribution is only due to the surface scattering? Can you provide some insights about this decision in case we have different soil moisture levels and subsurface scattering? Can you also provide some comments about the role of vegetation moisture, SAR data, as well as the role of temperature?
Yeah. Thank you for the question. Yeah, we are assuming that for surface we only have for soil we only consider the surface mechanism due to the fact that we chose L band, and with the L band we have a degree of penetration of the signal, but only in the very top layer. For instance, instead, when using P-band data like biomass, I was at the Polinsar conference a few months ago, and they were showing that with P-band you can really detect some volume scattering below the surface. What we assumed is that again, of course, with L-band we have some degree of penetration, but we assume to consider only the surface scattering. And for the vegetation, of course, the moisture inside the vegetation has an impact. That's why we are also using as input for the framework the vegetation water content, trying to give the model information about the water content of the vegetation and disentangle also this effect. About the temperature, again, in the inputs we consider also the temperature, the 2-meter temperatures from ERA 5 to attempting considering also the variations in temperature, in that case of the air, but which has of course effects on the temperature of the plants and the soil, of course. I didn't if it's satisfied of the answer.
Let's see, but thank you.
Okay.
Are there any?
Yes, they're responding. Thanks a lot.
Okay.
That's great work. So, if anyone else has a question? Go.
Okay, yeah, but maybe I have a lot of questions, so maybe I can take them a bit offline.
We can ask one
Okay.
question online. And then
Yeah, I was just wondering as well if you looked with your methodology to forward problems. So you go, I mean, maybe so sure it's easier, but then if you start from the parameter and then have this physics informed machine learning model, and then try from there to infer the backscattering in a case where the equation might not be as straightforward. Have you explored this?
Okay, so you mean to use the AI framework of the last study or the previous?
Any of the methodologies you talked about?
Yeah, basically what we do here especially in the second approach.
Because I see that you can still reconstruct the backscattering.
Yeah, exactly.
With your simplified equation.
So,
but in cases where the equation would not be so simple.
So simple. Yeah, it's this is something also another finding of this research. As I was mentioning at the beginning, the problem is quite imposed, and also it's very difficult to find the dataset providing all the input parameters of the radiative transfer model, and that's why we chose to adopt a simplified version. And also in this case, it was difficult because sometimes we noticed that, for instance, we had much more overestimated volume scattering, and double bounce is close to, also surface is very low. So we are trying now to find solutions to avoid that the network swaps the different mechanisms, because we want consistency. We want consistency. So we didn't try really to run the forward problem. What we did, as I was mentioning before, was to here we run the let's say the forward model, the original one, not the simplified one, to consider some the soil moisture values we got in the in situ measurement data set, and we didn't have roughness measurements, so we had to randomize in a, let's say, in a good range, in a typical soil roughness range. So what we tried here was to run the forward problem and try to compare the results we got. But what I would like to say is that if we increase the complexity of the radiative transfer model, the inversion becomes much more difficult to perform because we have many parameters.
So if we don't have any more questions, thanks a lot, Lorenzo, for
Thanks to you for the invitation.